fact with the Rydberg atoms.
Thank you very much. I also want to thank you that you invited me to this nice workshop, and I'm quite happy to present our work here. So I'll talk about Rydberg atoms in ultra-cold gases, and actually I'll split the talk into two parts. So the first part is, which is also in the abstract and so on, which is the Trilobite Rydberg molecules, where I will not only show you how we excite them, but also quite a lot of how to calculate the potentials to be structured Rydberg molecules. And then in the second part of my talk, I will go to the Rydberg excitation in the Einstein condensate. So there are quite high densities involved and other effects come into play. And then I'll give you a short article. All of these experiments are done basically in the following setup. So there's a quite elongated cloud of rubidium 87 atoms. And yeah, we can go to with the Einstein condensate of about 1.5 million atoms, but of course we can also stop before the condensation, have slightly less dense clouds. And then we do our Rydberg excitation by a two-photon transition. And what is a bit special about our setup is that the second excitation beam is actually focused to the cloud, so we can address very high density regions in the center of the cloud. And actually this lens, which is focusing down this laser beam, is inside vacuum and also optimized for imaging the cloud in situ. But this I will not talk much about, but we have talked here. After we excite such a Rydberg atom, we field ionize them and we detect the ionic core on an MCP detector, and we can reach main quantum numbers in the range of like 36 up to 150, so then the exactly. So for the first part of my talk, I will not talk about a BC, but rather on a less dense cloud, which had about 2 microkelvin or so. And this is actually the regime where you can find Rydberg molecules. So Rydberg molecules consist of a Rydberg atom. So there is the ionic core and the electron, which is in this high-lying Rydberg state. But then there is a second atom which is still in its ground state, and it's actually bound to this Rydberg atom. And such forms of molecules. So we have to go to like high enough densities that there are already the atoms so close to each other that there are neighboring ground state atoms coming into the Rydberg orbit. And so what actually makes this bond for the Rydberg molecule is the interaction between the Rydberg electron and this ground state atom. And so we have to look a bit into detail of this electron-neutral interaction. So here I plotted the probability density of a Rydberg electron in the S state, and now we imagine that at some position there is this Rydberg atom sitting, and as there is a charged particle and the is neutral, there is a particle before potential. And in principle, one has to describe this like as an electron-neutral scattering, and describe it in S-wave scattering, P-wave scattering, and so on. But of course, for the P-wave and D-wave scattering and so on, there is some centrifugal barrier coming into play. And in our system, there is not enough energy to overcome the centrifugal barrier. So this energy is basically the energy what the electron brings into this collision, and we do it in some steady classical way. So we say, okay, when at the outermost turning point, the electron has 0 energy, but then when it starts to roll into the Coulomb potential of the ionic core, then it gains some energy. And this is the energy we attribute for this electron neutral scattering in the end. And this is, as I mentioned, not enough to overcome centrifugal barriers, so we only describe this problem as wave scattering. So we use a Fermi pseudopotential, and as I mentioned, this S-wave scattering length, but it is still not the very simplest description, because we put this energy dependence of the electron already in this case. And when one now integrates over all like possible positions of the electron, basically you get this interaction potential between the electron and the neutral atom. I'm sorry, it is so the energy, so depending on the internuclear distance between the Rydberg core and this neutral perturber atom, at positions where the electron is very likely to be, there is a lot of interaction going on, and therefore the potential gets deeper, and at positions where the electron is less likely to be, it's smaller, and therefore this potential looks very similar to the radial part of the electron wave function. And the fact that it differs in here is this K dependence on scattering. And so at very large distances, this asymptote of course corresponds to the state where this perturb is outside the Rydberg orbit and we just excite a normal Rydberg atom. So this is also what we defined our zero in our experiment. So the fact that the signal where we just excite a normal Rydberg atom. But then on radial tunings with respect to this line, we see the Rydberg molecule lines popping up, which correspond to a bound state in this potential in the Hamiltonian spell. And we cannot only see like dimer Rydberg molecules, but also trimer or tetramer. And so these are the standard S-type Rydberg molecules. But if you now do not concentrate on this S state, but you include all the other states as well, it looks the following. So the states are of course split due to quantum defect, and the potential I showed you up to now is like a very tiny perturbation on top of this line, so it's megahertz, and splitting of these lines is of course gigahertz. But you can already see that there is some strange molecular state appearing, which has also gigahertz binding energy up there. And this is the so-called Trilobite state, which Chris Green has already proposed in 2000. And the special thing about this Trilobite molecule is that it's highly polar. So the molecule will look such that there is the Rydberg ionic core sitting here, and the perturb atom is sitting there. And actually, all the probability density, or most of it, of the electron is located at the position of the perturber, and therefore you get a highly polar molecule. And so it would be very nice to excite such a molecule, to have a polar molecule to experiment with. And actually in the cesium, they are lucky because there the splitting between the S state and this Trilobite state is very small due to their quantum defect. And then they could already show in 2015 that you can excite such Trilobite molecules, but in general it's of course very difficult to excite because it has, due to this strange shape, it has no S character basically. It has very high L character, and you cannot directly excite such a molecule. And so we found some trick how to still do it in rubidium. But to explain this to you, I have to tell you a bit more about this, how to calculate these potentials and what further terms to include. So one of these terms is tolling. So I told you that P-wave scattering is not relevant in our case because there's the centrifugal barrier. But actually in rubidium there's some resonant state, or there's some bound state behind the centrifugal barrier. And once the electron has the right energy to resonantly couple to this state, we get this P-wave resonance, and then this can shift our potentials around a bit. So that's why we still need to include P-wave scattering, even for it's only relevant of the case of this resonance position. And when we do this, then there is actually some strange additional state coming down, which is also named after an animal, and it also has a very peculiar electron distribution, which looks like a butterfly if you want. And actually in Herwig Ott's group in Kaiserslautern, they've shown last year that we can excite this state. Even it also has a very high L character, but as it's close to this P state down here, it has enough P admixture that they could directly photo-associate such butterfly molecules. In addition to that, what also needs to be taken into account in these potentials is the spin degrees of freedom. So up to now, we only consider triplet scattering. So in our experiment, we have a magnetic trap. We have only a spin polarized cloud. So we have all atoms in the F equals 2, Mn equals 2 state. And then we can excite the Rydberg atom to the also spin up state. But of course, if we change the polarization of the laser, we can also excite it to spin down state. And then actually you have access to the singlet scattering channel. So you have to decompose the state into its triplet part, up, down, plus, down, up, and its singlet part, up, down, minus, down, up, and you put this into your calculations. So for all this S-wave scattering and the P-wave scattering, you have both singlet and triplet terms. And now you see there are also things coming into play where the ground state spin is pointing down. So we also have to take into account the hyperfine interaction of this neutral perturber atom in its ground state. And yeah, so this is what it looks like in the end. We have this hyperfine interaction, as I just told you. We have the electron scattering between this Rydberg electron and the neutral perturber atom, which is single or triplet, and we have the fine structure of the Rydberg atom very close to this spectrum. And so when we now look at the full calculation, we would get our final potentials. It's the following: we have this bare Rydberg atom, we have the S-wave scattering for both singlet and triplet, we have the P-wave scattering for both singlet and triplet, and we have the hyperfine interaction of the ground state. And as in our experiment, we have this magnetic and electric fields. We also put this in. And so how this spin story changes the potentials, I want to show you, like, this is still the plot we had before. So there is, as you see, there is this Trilobite molecule state up there, and for the 50S state, it's split by about 7 gigahertz with respect to the S state. And now when we bring all the spins into play, of course, there's also the hyperfine splitting of the Rydbergs coming into play. And this is actually 6.8 gigahertz. So that's actually the case why I keep showing you 50S potentials, because there this hyperfine splitting gets almost resonant, or resonant with the splitting between the S state and this Trilobite molecule. And when we do the full calculation, we do not only take into account so this is the picture when we have only the spin up state for the ground state atom, but now we get like a full set of these curves again for all the ground state atoms in the ground state. And so what we make use of now is there is some weak coupling over all these terms between the nuclear spin of the perturber atom and this orbital angular momentum of the Rydberg atom. And as the precession frequency of this nuclear spin gets so close to the splitting between these two lines, we can actually induce some coupling via this spin orbit, nuclear spin in orbit. So when I now include like the second set of potentials and zoom in on this upper part, then it looks the following. So we have again this hydrogen-like manifold of the Trilobite molecule and the S state, and then we have the hydrogen-like manifold of the other ground state manifold, and also the Trilobite state. And here you already see the crossing. And this is the point where we want to work at, because there actually the normal S state potential is crossed by this Trilobite molecule, and you already see that it strongly changes the shape of these potentials, and that we can find positions where there's a lot of S character, but still there's a lot of change or modulation of the potential due to the fact that there's this Trilobite molecule. And when we now look at the electron wave functions for these different cases, so here you can just see the wave function of the normal S-type Rydberg molecule. Up here you see what such Trilobite molecule looks again, or in this case it's still a bit of S character, but the one we want to actually excite, it's sitting down here, so it has significant S character such that you can easily couple to it with our two-photon excitation, but it also already has a lot of polarity, or like a lot of electron mobility at the position of the perturber. And yeah, so we expect this signal to show up actually at fluid tunings with respect to the line, so the potential is not like going down as for all the normal Rydberg molecules, but it's actually going to the blue side. As I mentioned in our experiment, we have to include magnetic fields, so the lines get split into 10 lines, but due to laser polarizations we can only excite some of them, which makes life easier. And then you can calculate the bound states in these potentials and compare this to what we measure. So this is what the data looks like. Here is the normal Rydberg line for the spin up case. This is the normal Rydberg line for the spin down case, which is just split by the Siemens splitting. And on the red side, respectively, there are the normal Rydberg molecules. But then here you can find this peak at fluid tunings, and this must be related to the fact that there's this Trilobite coming in. And of course we calculated many states, and somehow there's only one distinct peak, but then there's some broadening to the left. So we were wondering which of this wave function is probably the closest to what we see in the experiment. So we calculated the binding energies for the states and also the dipole moment. And the state up here looks like it's getting close to what we see. So we would expect that this, which is actually a hybrid of an S-type and a Trilobite molecule, has a dipole moment of already more than 100 dpi. And this is what we tested then. So we applied some electric fields, and actually apply very low electric fields. It's only a few millivolts per centimeter of field, and the line already shifts by more than a megahertz. And from this we can deduce a dipole moment of about 130 dpi, roughly. And yeah, so to give you an idea of how crucial it is that this coupling is resonant between the nuclear spin and the orbital angular momentum, we also took spectra for the neighboring quantum numbers. So for 49, the Trilobite is actually passing way up here, like at +60 or so. And so there's no crossing between the S-type molecule and the Trilobite molecule, so it only pushes the potential a bit down. But when we go up to 51s, then it's actually crossing right at the position where this outermost well typically is, so we don't see any normal Rydberg molecules anymore on the red side, and there's like maybe a bit of signaling. So this is like due to the fact that the Trilobite state gets basically out of resonance of this energy of the nuclear spin. So all this about the Trilobite molecules you can actually also read in our publication, which came out today. And yeah, I want to also mention all team members. So it's not only me, but of course also Florian, Chin, Felix, Robert, and Tillmann, and especially Florian worked a lot on the calculations as well. And all of this work was done in collaboration with Georg Dipole in Michigan. So he had the initial idea when looking at some potential calculations that this could work out. So yeah, he was visiting us last year for a while within the framework of the Jared program, which now came up in Germany and is funding Rydberg work there. Okay, with this I want to come to my second part of the talk. So up to now I've shown you like this normal Rydberg molecules more or less, where you have 1 or 2 or 3 atoms within the Rydberg orbit, and they are bound by binding energies of like a few megahertz. But now when we go up and we put more and more atoms inside the Rydberg orbit, there are actually line shifts occurring in the spectra which cover like a lot more, so up to like 50 or 60 megahertz. And so this like side feature here is coming from the thermal atoms around the cloud, but the VC is giving us this very large shift. And now we were wondering how to explain this large shift, and so we compare different main quantum numbers and what this shift looks like, and we find that the line is asymmetric, and that basically the main amount of shift stays the same for all n quantum numbers. So for the Rydberg molecules, of course, the binding energy depends on the n, but once you go to this very high density region, there's no like scaling with n or n squared or whatever, but it's always almost the same. And this is actually due to the fact that the same way the potential gets shallower, so then the binding energy of a single Rydberg molecule like reduces, but in the same way the orbit gets larger, and then there are many more atoms inside this Rydberg orbit which contribute to this overall shift. So basically the fact that this stays almost the same is related to the fact that the electron function is normalized. Yeah, and to fit the exact shape, or to explain the exact shape, we started again with this very simple calculation in S-gas gathering only. And we integrated over like all possible particles which are inside the Rydberg orbit, and with this you get the, like when you put in the peak density in our sample, you would expect the maximum shift of like 50 megahertz or so, which has already been, so this kind of calculation has already been done like a long time ago, when they did similar experiments where they had Rydberg atoms in a really, really high density in a thermal vapor. And yeah, now we see that it does not explain a very large shift in our experiments. So we came up with our potentials again. So when we take the normal assay scattering theory and we check, okay, when we now randomly place atoms in our Rydberg orbit, how much potential energy can we gain depending on their position. So we sum up over the energy contributions from atoms from different positions and we calculate that line shift. And the same way we do it with the potential where the p-wave scattering resonance is actually included. And then you can see that there is this straight butterfly state crossing, which I told you already before. And in this case, they can actually, single atoms which are placed close to this resonance can lead to a large line shift. So when we sum up all the contributions in this case, we expect much more line shift than we would expect for the single axial scattering only. And so this is what it looks like when we compare it to the data. So the blue line is just the assay scattering, and the fact that it looks different from this single line I had before is due to the fact that now this k dependence in the scattering length is included. And but when you include the p-wave, the scattering resonance, then you actually can also explain the white green. But it still does not really fit, especially for large main quantum numbers. And this is of course not so surprising if we have a DC and throw particles into some potential. So there's some more elaborate theory actually by Richard, and you can read about it in this paper. And with this I want to thank the team who was working on this part of the experiment, which is basically the old team. Most of them have left by now. And actually Michael was doing lots of the work, and he just graduated last year. And with the theory, he had some support from his screen synthesis. And now I want to show you what we are aiming at the moment with our setup. So there's the idea that when you have this Rydberg excitation inside our Bose-Einstein condensate, and the Rydberg orbit size gets comparable to the gets several microns large, then also there's again this interaction between the Rydberg electron and this BC, and the BC atoms start moving into the potential wells which are created by this electron. And when you wait for some time, the density of the BC should show some modulation which resembles the shape of the orbital. So when you put an S-wave or an S-state atom in there, the density modulation should be round, and when you put some D-state atom in there, you should be able to see maybe some structure. So we have done simulations, and also our colleagues have done some calculations, and it should be on a scale where you can really image this modulation of the BC due to the Rydberg imprint with our in situ imaging. So we are working on our in situ imaging and alignment and so on, and we hope to see this. And in preparation to do this measurements, we also did some measurement of the lifetime of the Rydberg atoms inside the condensate. So in the condensate, what is basically limiting the Rydberg lifetime is L-changing collisions. So when the atoms collide and then one of them is changing or when the Rydberg atom is changing its L quantum number, then actually it also gains some kinetic energy and it just flies out of the cloud and we lose it. So, and this L-changing collision time we measured for a wide range of n quantum numbers, and as I mentioned, we want to go to higher many quantum numbers to have a large Rydberg orbit, and actually we are quite lucky that in this range of the high quantum numbers, the lifetime is more or close to 10 microseconds, let's say, and this can already be enough to imprint this wave function of the condensate. So with this, I want to summarize. In the first part of the talk, I've shown you how one can hybridize S-type Rydberg molecules with Trilobite molecules, and use this spin-orbit coupling basically of the nuclear spin with the Rydberg orbital angular momentum to hybridize these two states. And we have determined, so we have seen this Trilobite state experimentally, and we've also determined its dipole moment. And in the second part of the talk, I showed you what happens if you put a Rydberg atom in a very high density environment in the EC. Thank you for your attention.
So what would be the typical lifetime of such a trilobite molecule or hybrid? Say if it's highly polarized.
Yeah, so the calculated lifetime for like this state was about 1.3 microseconds. And so the line width in the experiment looks a bit broader, but I'm not sure if this is due to residual electric fields. So if I don't convince them perfectly, then the line's already getting a bit broader. But it's like, yeah, on the order of a microsecond.
I can really provocative questions. Maybe you already answered. So, like office with Trilobites, all of this kind of fancy kind of molecules, so this fancy wave function. How do you actually know that you create them? What I mean is like, like these pictures, the electrical pictures look amazing.
Yeah.
And I think your experimental data are convincing, but of course, like, it's not. How do you know you excite, for example, the specific pure state rather than some kind of mixture or variety?
We don't know. We only know that it has a large dipole moment, which is a good indication that it is some Trilobite molecule, but if it's really purely this state, no.
So is there a way to actually reach some kind of wave function or something? I think it's a little bit cool.
Yeah, but the question is if the resolution is good enough. Yeah, because to excite, so what I did now is like a 50S Trilobite, basically. And then when you go up higher in N, then at 70, you can enrich again some situation where the 70D state gets in resonance with the Trilobite and so on. But this is still, the orbit is not large enough to image it optically. And maybe it works again. But then, yeah, I didn't. So the calculations take long and long at the higher the N, and so I didn't go up further to check when it would work again. But maybe one can go to situation.
I think I discussed this with Misha some time ago. I'm a little bit confused about this experiment sometimes. I mean, shouldn't the states you create be very, very complicated? Because somehow, I mean, there's also blockade radios and so on. Shouldn't you be in some sort of a super molecule or some kind of strongly entangled state actually instead of?
So we actually have really low power in this experiment. So we do many excitations, and we always do like one excitation and then we do ionization. So there should never be like 2 or 3 of these molecules present in the same experiment, because we do very low intensity excitations and then we either get 0 or 1, just to avoid this like complications.
But still, for example,
yeah,
atoms interact, right? I mean, even if for one Rydberg atom, you have polarized atoms, which, VC atoms, which could talk to each other or compete for this. I guess it's a little bit what we heard that.
Yeah, so we included these effects in our quantum calculations, and they reproduce the spectra extremely well. Of course, what we don't include, for instance, are like really effects of phonons, but they live on a totally different time scale, like on kilohertz energy. So that doesn't matter. But it's true. It's in principle you have to consider all possible many-body states, but the question is how relevant are they? And I agree that it's not that relevant in the end to get the basic profile right. And it's always a matter of what are the energy scales or the time scales corresponding to those many-body states.
All right. So, if there are no further questions, stay.